Hey everyone, and welcome back to another video. I know it's been some time, but I figured that since, it's been more than a year by now, I might as well just put out a new video. Uh, Today we'll be going over the last four problems from the FMA 2022A exam. Yeah, so hopefully you guys enjoy and find it somewhat helpful. And yeah, without further ado, let's get started. So, the first problem that we'll be taking a look at is problem 22. And pretty much the setup is you have these two wedges with masses m and angle theta. And then on top of them, you put a block of mass 2m. And pretty much what it's saying is when the system is released from rest, what is the downward acceleration of the block? So of the mass 2m, what is the acceleration? And pretty much the main idea for this problem is you kind of use some weird conservation of energy stuff. So what you do is, let's say that the top block of mass 2m moves down by a distance of x. Then what you do is you find the velocities of all of them, and you can basically, if you find the velocities of each block, you can find the total kinetic energy, and and then, yeah, you can pretty much use some like weird conservation of energy stuff. So, I have made a diagram here so it's more clear. So, this is just to relate the velocities. So if we let the velocity of the block be VB, and then the velocity of the ramp be VR, um, if we take a look at this diagram, let's say that we move the block moves down a distance of x. Then we can see over here that this ramp moves to the right by some distance y. And we have some parallelogram that's right here. Okay, so this is distance of y, and this block moves down a distance of x. And so we see we have a parallelogram and we also have a triangle here. So because for parallelogram, this side at the bottom and this side at the top are going to be the same. So this is also going to be y. And this triangle is also going to be similar to the ramp. So this angle right here is going to be theta. And I drew it in more detail down here. So this triangle right here, with the distance downwards as being x and the distance to the right being y, see it's right here. So if we use trig, we see that the tan of this angle theta is equal to y over x, right? Because opposite over adjacent. And pretty much if we, since you know that velocity is, if you know calculus, velocity is the derivative of position, or if you don't know calculus, velocity is pretty much going to be related to your position only by like a factor of time. So this we can just replace the distances by the velocities and it will give us the same relationship. So it'll give us tan theta is equal to the horizontal component, which is equal to the velocity of the ramp over the vertical component, which is the velocity of the block. And so we can pretty much find the total kinetic energies. So we can say KE is equivalent to 1/2 times the mass of the larger block, which is 2m, times the velocity of the larger block, which is VB squared, plus 2 times 1/2 times the mass of the ramp times VR. And the reason we multiplied by 2 at the beginning is because there are ramps on both sides. And now we can plug in we know that VR, which is our ramp, is equal to V block times tan theta. So we can plug that in into VR right here. So this means that the kinetic energy is equal to mvb squared plus m times tan squared theta times vb squared. And now we can use the following trigonometric identity that 1 plus tan squared theta is equal to secant squared theta. Or that's the same thing as 1 over cosine squared theta. So now this just means that if you factor out the mvb squared, that your kinetic energy, or Ke, is equal to mv of the block squared over cosine squared theta. And honestly, by this point, if you looked at the answer choices, which I don't have here because, well, the ones that they put on the website already had the answer choices, like the correct one marked, and I didn't want to put that there. So if you look at the answer choices, there's only one answer choice that has cosine squared theta in it, and so yeah, that would just be your answer. But if you wanted to go further, you know that um this is the same thing as a block. We can basically model this entire system as one block with some effective mass m, EFF. So the way we do this is let's say that this entire kinetic energy can be modeled by some block that's just falling down. So this has an effective mass MEF times V squared. And so in this case, M effective is going to be equal to M over cosine squared theta. And we also know that this kinetic energy is coming from the block going down in distance x. So this kinetic energy is also equal to mg times x. And this is also going to be equal to your m effective times your g effective times x. And since mg is equal to your effective mass, which is equal to m over cosine squared theta, this means that your effective acceleration, which is g effective, is equal to g times cosine squared theta, in order for the cosine squared thetas to be canceled out. So that's going to be your answer, g cosine squared theta. All right, so for the next problem, we're going to move to problem 23. And pretty much, honestly, in my opinion, this is probably one of the cooler problems, which is it was pretty unique. So uh, you're given two situations in this problem. So the first case is you have air resistance that's proportional to the speed. So I'll do A. So for case A, actually no, I'm not going to do that because the names of the objects. I'll just write linear. Okay. So linear, and then so for this one, your force of air resistance is going to be proportional to your velocity. And then for quadratic, which is the other case, your force is going to be proportional to your velocity squared. If you want to read the entire problem, I'd recommend pausing beforehand or taking a look at the website. So yeah, so you have two cases given in the problem. The air resistance force is proportional to velocity, and another one is air resistance is proportional to velocity squared. And then you basically have two objects. Object A is going to be thrown with some initial horizontal velocity v. So I'll just draw here. So you have A, which is thrown with v, and B is just going to be dropped from rest. And so you want to find, well, it tells you the times that the objects hit the ground are going to be times TA and TB. And we basically have to account for this air resistance and see the relationship between the times in whether the air resistance is linear or if it's quadratic. So in the case where there is no air resistance, the objects will hit the ground at the same times, right? Uh because you don't have your vertical component is independent of the horizontal one, right? Like whatever velocity you're moving in the horizontal doesn't affect the your vertical component at all. But with air resistance, it's a bit different. So let's first take a look at the linear component. So let's say this block, well, actually, let's start with block A, okay? So for block A, we have, let's draw our thing, and let's say in some path of its motion. So the block is right here, okay? And it's proportional to velocity, right? So your drag force is going to be acting behind. So if we magnify this up, we see it has that. So your force is going to be pointing in the opposite direction of the velocity. And so it's going to have your horizontal component and your vertical component. So let's just say that the force is equal to some constant A times V. All right. So this means that this is A times V. And let's say that this angle here is theta. So then your horizontal or your vertical component is going to be AV times cosine theta. And then your horizontal one is going to be AV times sine of theta. But the thing that we notice here is that V cosine theta is actually the same thing as just your vertical velocity. And V sine theta is just the same thing as your horizontal velocity. So we can rewrite this as A times your horizontal component and A times your vertical component. And pretty much what this means is that as like the forces on the horizontal part and the forces on the vertical part only depend on the horizontal velocity for the horizontal component and the vertical velocity for the vertical component. And that means that even though there's a drag force, it's still independent of the direction. Like the horizontal component is still going to be A times your horizontal velocity. Like your force in the horizontal part doesn't depend on your vertical velocity at all. So your forces in the vertical and horizontal are independent of each other. And so as a result, since your horizontal part doesn't matter at all, this means that if you were to drop a block from the same height, right, with no initial horizontal velocity, it's going to reach the ground at the same time because your horizontal part doesn't affect your vertical part. And the only part affecting the time is your vertical component. So we can cross out uh B, D, and E because TA has to equal TB for linear. And now for quadratic, if we kind of do something similar, so instead it's going to be A times V squared. We have our two components. So A V squared cosine theta, A V squared sine of theta. And so here we see a bit of a problem because in the case where it's quadratic, you can't just replace V squared sine theta with Vx, right? Because Vx is V sine theta. I'll write at the top, Vx is V sine theta. So if you square that, you get V squared sine squared theta. So your vertical and horizontal forces are not only dependent on your vertical part, they might also depend on like the horizontal part of your velocity. So for your quadratic, it's not going to be um it's the two directions are not independent of each other. They depend on each other because they depend on like theta, right? Like if we could rewrite this as like Vx squared over sine theta, but it still depends on theta. And theta will depend on your relationship between your vertical and horizontal components. So for quadratic, as you can see, your vertical and horizontal parts, the forces, they depend on both of the components, not just one. So they aren't independent. So as a result, TA will not equal TB. And so we can cross out answer choice A and we're left with answer choice C. And to see specifically why TA is greater than TB, or if you were to throw a block and it takes longer to reach the ground, it's mostly because of the fact that if you throw the block, you are gonna have a higher like force. You're gonna have a higher resistive force on the block, right? Because you have an extra additional horizontal component to your velocity. So you're gonna have a higher force because force is proportional to velocity squared. Instead, and as a result, the higher force is gonna act more on like the vertical component than if you were to just drop it off a building. And so as a result, you're gonna have more resistive force keeping it from hitting the ground earlier, for the one that's moving horizontal. So it's going to take more time for the horizontal one to reach the ground. Like if you throw it off the cliff, that one is going to take longer to reach the ground because there's more resistive force from the larger velocity. So for that one, the answer is going to be C. All right. So for problem 24, we have a satellite that's in orbit around a planet of mass m. The maximum distance from the center of the planet is d, and it's at that point it's traveling at a speed of 1/2 square root gm over d. What is the area of the satellite's orbit? So let me just quickly draw a diagram here so that it makes more sense. So we have an elliptical orbit because according to Kepler's first law, closed orbits must be ellipses, and the foci is like the planet that it's orbiting around is going to be at one of the foci. So this maximum distance right here is going to be d. And we know that at that point, the velocity is equal to 1/2 square root gm over d. And for these types of questions where it tells you the velocity at a certain point, you can use this equation called the vis-viva equation, and that pretty much says v squared is equal to gm times 2 over the distance you are from the planet minus 1 over the semi-major axis. And yeah, so all you have to do is plug in your value for v and your value for your radius, or like your distance from the planet, and you can find your semi-major axis. And once you find that, you're pretty much done, because after that, it's just properties of ellipses. So this equation, the vis-viva equation, is like pretty useful in this case, and in a lot of problems where you want to find the velocity at a certain point. So if we plug in our v and we plug in the d, we get 1/4 gm over d, right? Maximum distance, yeah. 2 over d. And so the gm's cancel out, and you're left with 1 over a is equal to 7 over 4d. Uh, yeah, 8d over 4, yeah. So your semi-major axis is equal to 4d over 7. So if we draw this on our ellipse, the semi-major axis is going to be from the center to the farthest point. So this distance right here is equal to 4d over 7. And this means that this distance from P to the center is equal to 3d over 7. But we also know that this distance from P to the center is your focus, because your planet is going to be at one of the foci of the ellipse. So the distance between your foci and the center is your focus, which is 3d over 7. And so now we can use the equation a squared equals b squared plus c squared, where a is the semi-major axis, b is the semi-minor axis, and c is the focus to find your semi-minor axis. So in this case, b squared is going to be equal to 4d over 7 plus, minus 3d over 7 squared, and that means that b is going to be equal to 16d squared minus 9d squared, 7d squared, so d root 7 over 7. And finally, to find the area of the ellipse, we can use the formula: the area of an ellipse is equal to pi times the semi-major times pi times the semi-major axis times the semi-minor axis, which is just going to be equal to, well, a is equal to 4d over 7, b is equal to d root 7 over 7. So your area is going to be 4 pi uh, d squared root 7 over 49. And if you look at the answer choices, uh they actually write it in a different way. So if we divide the numerator and denominator by, or multiply the numerator and denominator by root 7, you get 4 pi d squared times 7 over 49 root 7. And the 49 and 7 cancel out, so you get 7 in the denominator. So you get the final area is equal to 4 pi d squared over 7 root 7. or 4 pi d squared over 7 times the square root of 1 over 7, which is, I think, the form they have in the problem. Right, so for problem 25, we have cylinder is placed with its axis vertical and a rubber band of mass m and tension T is wrapped horizontally around it. What is the minimum coefficient of static friction, mu, between the rubber band and the cylinder such that the band will not slide down the cylinder? So if we draw our cylinder here, right, we have cylinder and then we have a rubber band that's around like this. And so the reason why a cylinder won't slip down if you, or I mean, if the rubber band won't slip down if you tie it around the cylinder is because the static friction, pretty much, if your rubber band's gonna exert force on the cylinder, right? Because if you think about it, right, if you wrap something around something else, it's gonna like try to squeeze it. So there's gonna be some pressure between the rubber band and the cylinder, and so that pressure results in a force. And that force is what's keeping the rubber band, um that normal force is what results in the friction force, and the friction force is balancing the weight, which is why it's being kept upwards, because of the friction force balancing the weight from the normal force. So the first thing that we want to do is trying to find this normal force. And the way we're going to do this is by just looking at an energy standpoint. So suppose we were to expand the radius by some delta r. All right. So that means the length of the cylinder would, I mean, the length of the rubber band would be changed by a distance of 2 pi delta r. And so this means that the work done by tension, which is just equal to force times distance, is going to be equal to tension times 2 pi delta r. But at the same time, you're also going to have, uh, since it's in static equilibrium, you're going to have pressure from the surface of the cylinder, which is pushing outwards on the rubber band, which is why it's causing it to expand by delta r. So we can also find the pressure and from this, because we know that the total work, so delta W, is going to be equal to 0. And this is equal to the work done by the tension plus the work done from pressure. And so, or actually technically minus because they're in opposite ways. So this is going to be 2t times 2 pi delta r minus the work done by pressure. So the work done by pressure is equal to P, or I'll write it here. So the work done by pressure is equal to P times the delta change in the volume. And so the change in the volume is going to be equal to P times, and let's just say that this rubber band has some area of A. So like this area around it is area of A. So then it's going to be P times A times delta R, right? Because volume is equal to A times delta R. So if we plug in this value for work, we get P times A times delta R. And that means that your pressure is going to be equal to 2 pi T over your area. And since force is equal to pressure times area, right? That means that your force, which is your normal force in this case, so your normal force is going to be equal to 2 pi T. All right, and now we can just use Newton's second law. So we know that the sum of the forces in the y direction is 0 since it's in equilibrium. So that means that your friction force is going to be equal to mg. And your friction is equal to N times mu, right? Because, well, that's your maximum friction force. Your maximum static friction force is equal to your normal force times your coefficient of friction. And so setting these vertical component, the total vertical force equal to 0, we have mg is equal to n mu, or ng is equal to, if we plug in n, 2 pi t mu, and solving for mu, we get mu is equal to mg over 2 pi t. which is the answer. Answer choice A. Alright, so hopefully this video was informative, helped you guys solve a few problems. Let me know if you have any suggestions for other videos. I'll see if I'll make a few more in the future. Uh, and I'm planning to do a live solve of the 2022 B exam sometime before the FMOD for 2023. So yeah, thank you for watching, and I will see you soon.